Hi everyone, it's Peter here again from Lucid Motors. And here I am standing by two great examples of Lucid Air. We have a Grand Touring here, resplendent in stellar white, and a Touring here in this zenith red. Now, Lucid Air has broken so many boundaries. It's been the first car to achieve over 500 miles range on an EPA. It's been able to charge 300 miles in just 21 minutes. And it fuses two distinctly disparate attributes. It's got the interior space of a luxury German Grand Marquis automobile, and yet it's got the handling dynamics of a sports car. How on earth did this come about? Was this chance? Was this happenstance? No, it's truly been a labour of love for the whole team here at Lucid for many years, and it was born of a clear vision of how we were going to truly advance the state-of-the-art of an electric car. And I've been waiting for this moment, a moment when Lucid Air is now in the hands of customers to feel that we've kind of earned the right to explain how we achieved that. So let me take you through this story. It started many years ago when I was approached by a little company called Ativa, about 20 people. Would I join and want to do an electric car? And I didn't want to just join the bandwagon. A lot of people were doing EVs for the sake of it. I feel passionately about the environment, and I feel passionately about the scope for advancement of EVs. And those two things are synergous. By advancing the state-of-the-art of an electric car, we can lead to catalyse the mass adoption of sustainable mobility. We can drive the prices down through the technology. And in order to do that, I felt passionately that we needed to move the technology on. And to do that, we'd have to do all the tech in-house. In-house technology, more advanced technology than ever anyone had achieved. And to make more compact, more energy-dense and power-dense drive units, to have a sculpted battery pack around the interior space of the car, to create more efficiency, because efficiency is the key driver to drive down costs in an EV and lead to a more widespread international adoption of EVs. So here I am, reveling in the luxury, comfort and sheer spaciousness of the rear seat of Lucid Air. And in this instance, it's a Grand Touring with an epic Santa Cruz interior. And I'm indulging in my little 3D classic wooden puzzle here, which I find absolutely fascinating. But more of that later. Now, you may say with my mere 6-foot frame, I'm not best equipped to judge the space of an interior. So luckily today, I'm joined by two dear colleagues, Mr. Mike Bell, who heads up digital here at Lucid, and Mr. Zach Edson, who heads up sales and service. Gentlemen, you look better qualified. How tall are you?
6'7". 6'6".
You're qualified. Please take your seats.
Okay.
Okay, I'm settled and comfortable up front. How's it in the back?
It's fantastic. I may fall asleep. It's so comfortable.
Hey, steady on, Mike. There's work to do. Do you find it satisfactory?
It's wonderful.
Yes.
Please, thank you. So I find that a fascinating proof point. 6'7", 6'6", two former basketball players finding the interior space of a Lucid Air satisfactory. So back when the Space Concept was conceived, this whole notion of a car which was smaller on the outside and bigger on the inside, I can't tell you, the number of people said to me, well, why do you want to make it smaller on the outside? Yeah, people like big cars, don't they? It's going to be a big limousine. And I said, look, I want to create more of a driver's focused machine. But I confess there was an ulterior motive. I wanted it more agile so it could do this. And this. And this. So how do we even start conceiving a car which is smaller, more compact on the outside, bigger on the inside? Let's look at some of the core geometries of that car, the overall length, the position of the wheels, the available space for the cabin, and then we can start wrapping in some of the other factors like a miniaturized advanced electric powertrain. Let's take a look at some of these variables that we can adjust and really things that we can use as tools to our advantage. So we have the overall length of the vehicle. That's a consideration. And it was important to minimize that. But also we need to consider the wheelbase of the vehicle, which is the distance between the front and the rear wheels. Maximizing that is important in order to create maximum cabin space, but not going too far. Generally speaking, longer wheelbase creates more stability, shorter wheelbase can give more agility. And how can the people then fit into this space? We need a driver to sit here. And a rear occupant here. So we start looking at some of these core fundamentals, and the rear occupant may want to adopt a more upright position here, or may want to adopt a more reclined position like that. So these are the fundamentals that we start laying into the car. And we look at the eye ellipse and the legal eye angles, the vision angles, and we look at the reach for the driver and the steering wheel position. These are key factors to consider. And we generally design for a 98th percentile occupant size here at Lucid, which means that only 2% of the population is larger statistically. So really, to minimize the overall length, maximizing the wheelbase, and maximizing the space for the occupants within that wheelbase, there are some critical sort of touch points that we need to consider in the packaging of the vehicle. Clearly, it's important to have reduced overhangs at the front and rear. Minimize this overhang distance, which gives great proportion front and rear overhangs. Maximize the wheelbase here, which we'll refer as wheelbase, and then the overall length. See if we can reduce that as much as possible to create this super compact, sporting luxury sedan. And really, the search was on how do we optimize key points. One was the relationship between the rear occupant's H point there, which is the hip point of the rear occupant, and the rear axle line here, the center of the rear wheel. That relationship is absolutely critical. And we looked at the three-dimensional package, how to minimize this and maximizing safety considerations, noise and vibration, and body engineering packaging with rear suspension. And the other critical area is the relationship of the front occupant's foot with the front wheel. Now, normally, in a gasoline car, we don't really consider that so much because there's an engine here and a transmission. So we have a gasoline engine here and a transmission housing. And really, that's what tends to drive the driving position rearward, rather than the relationship of the driver's foot to the front wheel. Now, to explain that, I can best do that on the Leap platform itself. So come with me and I'll show you that for real. So here we are with the Lucid Electric Advanced Platform. And first obvious point is we don't have a gasoline engine, we don't have a big transmission. So what really constrains the position of the front occupant and the driver relative to the wheel really is the structure that runs through here. And why is that important? It's critical. Because this is the transition point, this very point here, between the safety cell of the car, which needs to be rigid and to protect the occupants, and the crumple zone here, which needs to be something very different. It has to be soft, compliant. Just as a mattress, if you were going to jump out of a window, you need that softness of the mattress to absorb the impact. This needs to be soft and impact absorbing. This needs to be rigid to protect the occupants. And at this particular transition point, we really need to make that super strong, because this is where the key loads that are imparted through the crumple zone into the safety cell, and this is where the maximum forces are seen. And this is why we have this triangulated structural feature here. It is the relationship between that structure as ability to absorb loads and the occupant's feet and the wheel, which is a key determining factor in how we can get maximum interior space for a given wheelbase. An interesting sort of fun fact here, we even use the Wonderbox here, not just as an electronic masterpiece, but we use it as a secondary bulkhead structurally to enhance the triangulation at this interface. Let me explain in more graphic detail. So let's take another look at this crucial interface between the crumple zone and the safety cell and how that influences foot position. So here we have at this crucial interface the triangular forces, the forces coming in from the crumple zone, triangulated by both the cross member, augmented by Wonderbox, and what we call the torque box casting. And this determines effectively how far forward safely we can position the front occupants in the space concept. So armed with these relationships, the relationship between the driver's foot and the front wheel, and the relationship between the rear H-point occupant and the rear wheel, we can have a determined relationship between cabin space and wheelbase. What else can we do? We need to minimize overhang, particularly front overhang. And that leads to the next piece of the puzzle, the front end module. Let me show you that now. So here I am with the Lucid Air front-end module. This is super compact, super complex assembly of so many systems, all combined and housed in this large, expansive, injection-molded element. Let's take a closer look. So there's so much to tell you about the front-end module. Maybe I'll start with the multi-lens array headlamps, nearly 9,000 micro lenses, the most homogeneous light field on the market today with digital switching technology. And then we've got the sensing capability, long-range radar for ADAS here, augmented and complemented by a 120-degree solid-state LiDAR system. And we've got local short-range stitch radar in the corners here. The bumper system is central. It's an aluminum bumper with an energy-absorbing foam cover. But a feature I'm particularly proud of here is this Vortex Induction system for our cooling. These vortices let air in through the active grille shutters, computer-controlled shutters, and the air spools up in this vortex and spins out onto the radiators, one either side. Let me take you around the back to show you that. And around the inside here, we see the rear surface of the aluminum bumper, and we see the vortex duct and how it leads to a radiator. Now, we've removed the radiator from the right-hand side for visual clarity to see the shape of that vortex duct and how it flows the air into the radiator. And this is all housed in this expansive black plastic injection molding. And in order to enhance the rigidity of that molding in the high stress areas, we've encapsulation molded plastic around this laminate of composite, which we call organosheet. Why was it so important to minimize the space occupied by all these systems? Not just to minimize the front overhang, but to provide space for the largest frunk of any sedan in the world. And that leads me to the frunk. Lucids, please display frunks. And here we see the expansive frunk of Lucid Air. And we've created a two-layer effect here with this shelf, which gives easy access for heavier payloads. But if I remove this top cover, you can take a look down here and just see the expansive frunk of Lucid Air, the largest frunk of any car in its class in the world. And just see the space that's enabled by the miniaturization of the powertrain through this bulkhead behind and the miniaturization of the front end module in front. Everything's been designed to the last millimeter. And if we look at the white car here, we can get an amazing insight as to how this has been achieved. You see here, behind the bulkhead which has been removed, the front drive unit, this super compact drive unit. We see the compressor for the HVAC unit here. We see the inverter here, and we see the twin blowers for our cabin ventilation system here. And this is all enabled between the two crush rails for frontal crash and the super compact front end module. So let's go and grab a frunk, shall we? Here it is, single injection molded plastic part. But hey, it won't quite fit. Why is that? We've actually created a shape which is undercut. It won't actually fit into the car without it being flexible. We actually squeeze it into a smaller shape, drop it in, and then it springs out into its final shape. And we've achieved this through a two-shot injection molding process, which has won a prize. And it really is commensurate with our philosophy of eking out every last millimetre of available space. So we've seen how these core relationships which define the space concept have been established. The relationship between the occupant space and the wheels, the wheelbase, the frunk, the front end module. And we see effectively, we started to design the car from the inside out. And I can't tell you how this breaks the mold. This is a revolutionary methodology. Most cars today are designed from the outside in. And in so doing, from this inside out methodology, designing around what is possible from electrification really breaks the mold. So the next step is for me to take you into the Lucid Design Studio to meet with our head of design, Derek Jenkins. And Derek will explain how he took some of this core packaging data and clothed it in the beautiful exterior and super aerodynamic shape that we know and love as Lucid Air today. So here I am in the Lucid Design Studio. We've got design downstairs, we've got advanced engineering upstairs, and I'm surrounded by some models that we used in the development of Lucid Air. We have some 1/3 scale models here, and we have a trusty old friend that we dug out of storage. This is the original clay model, full-size clay, that we used in the development of Lucid Air. And there's no one better to explain this in detail than Derek Jenkins himself. Hey.
Hey, man.
Hey, Derek. Hey. So this is an old friend of yours.
This is the original development model for Lucid Air. We only had one clay model, which is pretty unusual in the car business, but we did all the development work on this model.
So we broke the rules. We didn't design from the outside in. We designed from the inside out, but we still use a traditional technique with the clay.
That's right. I mean, it's still the best tool, I think, to really get the proportion right, do a lot of iteration, a lot of changes, a lot of refinement. But of course, we started on the inside, and we did that with the original seating buck, if you remember that.
Oh, yeah.
A lot of experimentation there.
We did, yeah. And so we positioned the front occupants close to the front wheel, the rear occupants close to the rear wheel.
That's right.
And then we had a sliding buck.
That's right. And that really allowed us to optimize the layout. It allowed us to get the head position correct so we could still have a very sleek, low cabin, get the rear seating position all the way back, and we just iterated until we got what we wanted.
And that finally determined exactly the wheelbase that we determined in the end.
That's right. And throughout that process, I think, as we were working from the inside out, the design team was sketching and working on what the theme of the car would be like, and that it just iteratively turns into scale models and then eventually full-size models.
So let's take a look at some of these 1/3 scales and some of the processes that you use here.
That's right. You know, this is our CNC milling process. So once we've created the data in the computer, we'll come in with a CNC mill and machine this out overnight, and then sometimes alter it by hand and bring it back into the computer and just repeat the process over and
here
over.
you've just got some rough cuts taking around the back here.
Yeah, that's right. When the clay is applied, and then we bring the machine in and machine it smooth, then you see this, and then we run it again with a finer tool path, and then that's when you end up here. And then the rest is by hand.
Right. So here in the studio, we use this modeling clay. And this is an engineer with a piece of clay, Derek. What am I doing wrong? This stuff's a rock. How do you do that? What am I doing wrong?
You need to get it nice and warm. We have ovens.
Look
Yes,
at that.
look at
Why
this.
is he doing it for you?
It's super pliable.
So go on, but be the master show us. Now-
You apply it accordingly, and it's been a few
Look at
years
that.
since I had to do this myself.
Oh, there's a touch of the
But
master there.
yeah, and then that cools down, and then you
cool
can
it down and then
machine
you
it
can
off,
machine it.
or you can hand shave it.
It has a completely different character and texture. This is room temperature, and that's oven temperature.
it's
and look,
incredible,
even I
yeah.
can do that.
Yeah, it's oil-based, and that's what gives you this nice, slick surface that once it cools down.
And the value is that unlike modeling something in marble or stone where you can only remove material,
That's right.
you can add back and you can go both ways. To your
And
heart's
you can
content.
recycle the material. So once the shavings come off, you gather it up. As long as they don't get contaminated, you can heat them back up and reuse it. It's fantastic.
So remind me, Derek, what am I looking at here?
Well, once again, a clay model, a representation of the Lucid Air interior. Just like the exterior, we use clay model to validate all of our data and all of our digital creation. And this is, of course, critical to get all the ergonomics, the seating, the posture of the steering wheel, the displays, all of that is figured out in the physical, along with all of our CAD work.
But we're not using clay for the seats in this particular
No, they
one.
tend to get your jeans dirty.
Yeah.
They're clay.
You had it from the
Yes.
man.
I've learned this over many years. No, of course, but we do develop the seat in a clay model as well. It's a combination of foam prototypes and as well as early clay modeling.
Now, let's take a moment to talk about aerodynamic efficiency and the space concept. So, although the coefficient of drag is widely quoted as the measure of aerodynamic efficiency, the ease of the car to cut through the air, there are actually two factors. There's the coefficient of drag, or CD, and we have to multiply that by area, the frontal area, to give the drag force. That is the amount of resistance that the car faces cutting through the wind. And here's a great example. We've got this 1/3 scale model here, and we've got the full-size clay here. And they are the same shape, right? They're identical shape. So therefore, although this model is 1/3 size, 1/3 scale, it has the same coefficient of drag, the same CD number as the full-size car. But because it's a 1/3 scale model, it has a 1/9 of the frontal area. So of course this induces 1/9 of the CDA, or drag force, of the total car. And because of the work we've done on the Space Concept, the car's smaller and has a smaller frontal area and therefore a smaller CDA. So whilst Derek and his team were developing the design theme of the Lucid Air, this exterior form, another team within Lucid was developing the most advanced, most compact electric powertrain imaginable. And with the belief that we'd be able to pull all this together to create the most advanced car. Let me take you through how that was undertaken. So in order to create Lucid Air, we had to do quite a crazy and radical process. We needed to create super miniaturized electric drivetrain, and we needed to design a car around it. And that would have taken years if we'd done it in sequence. A traditional company would have done that in sequence. Would have had to do an R&D program on the drivetrain and then see how that could fit inside the Space Concept conceived vehicle. Instead of that, we did the two activities in parallel. We split the R&D activity into two streams. We designed the car around the art of the possible, and in parallel, same time, we started miniaturizing the electric powertrain, going to ultra-high voltage, super condensed powertrain, the enabler for the very Space Concept to work. And thankfully, the two things came together to create the Lucid Air you know and love today. So from many years now, I've been drawn to the complexity and fascination of these traditional 3D wooden puzzles. And really, I'm almost simply in awe of the ancient minds that conceived such things long before computer-aided design was available or invented. So why do I find this so relevant to today's world, and particularly the design of the Lucid Air? Well, really, solving a puzzle like this is analogous to designing a car. Because designing a car is solving how three-dimensional entities fit relative to each other. Supposing this is the front suspension. Supposing this part is the battery pack. Supposing this part is the front occupant package. Supposing this part is the Wonderbox. Conceiving how all these parts fit together in a complex, single, unified, three-dimensional product is key and is really the essence of vehicle design, which we call packaging. Now, just imagine if I also had the freedom to determine the precise shape and size of each of these parts, which we do. The battery pack could be a bit bigger, a bit smaller. The drive unit could be slightly different shape. The suspension could be different types. Would that make the puzzle easier to solve or more complex? Perhaps I'll leave that to you to decide. So what if we could make crazy small motor drive units, electric motor, transmission, with the all-important inverter as an integrated unit, like crazy smaller than anyone else had ever done before? That would enable this Space Concept to come alive, to pop and really work. We didn't have the technology when we conceived this layout, but what if we could achieve that? What if we could create a crazy compact drive unit at the rear, maybe lay it down on its side and put the inverter here? What if at the front we could use the same unit, make it a little compact unit and pop the inverter on top there? What if we could create the most powerful, the most energy-dense, the most efficient drive units in the world off the scale that no one had ever done before? This is what would enable this Space Concept to work. And so I'd like to introduce our Lucid Integrated Drive Unit, which I have here. So unbelievably, within this classic aluminum flight bag, we have the Lucid Integrated Drive Unit with a power capacity of 670 horsepower. Here we see the key elements: the motor, the inverter, and the transmission stack either side. 74 kilos, up to 670 horsepower, super miniaturized. And look at the size of those drive shaft flanges. There's a clue that this thing has monumental torque output. And to complete the picture, we needed to integrate a battery pack which is truly sculpted around those occupants, around their feet and their legs. And we conceived a battery pack which is already traditional for an electric car, which runs the full length of the floor of the vehicle, but with the option to create this footwell for the rear occupant. And to gain some extra capacity, we're able to double stack elements of that battery pack right underneath the rear occupant's legs, like that. And this can be seen very clearly, this configuration here on the LEAP platform behind me. So here we see how some of the battery modules are configured at the underside of the LEAP platform. We have an additional module here at the front, creating a shallow tunnel. We have two double stacked here under the rear seat. And what's going on here? Well, of course, you don't actually have a car like this with this split. This is just to demonstrate. On the right-hand side here, we demonstrate the option of a battery with this footwell. And here we show the flat floor variant. This enables a 500-mile range car. This configuration gives exceptional rear seat ergonomics with 400-mile range. And I've got a Lucid Air Touring right here to demonstrate this footwell advantage. So here I am inside the Lucid Air Touring with the increased footwell enabled by the 18-module pack. And this car, even with this exceptional ergonomic package, still enables over 400 miles range. So I do hope you've enjoyed our little journey through the thought processes and the methodology that led to the creation of Lucid Air. And moreover, I really hope that we've been successful in achieving our objective in creating the next level electric vehicle. And why is that important? It's important because by demonstrating what is possible here today, this technology can transition down to ever more affordable forms of electric vehicle. And that in itself will make EVs more affordable and more available to more people, which will have a meaningful impact upon global warming.